power associated with a 600 ohm resistor, the characteristic impedance of audio transmission lines. So this is just a reference. For example, let's take an example. If you have a power which is 10 milliwatt, you can express this power in dB M scale as 10 log base 10 of 10. You just remove the milliwatt because you know that the unit of the resulting power will be in dBm. So log base 10 of 10 is 1 times 10, 10. So the result will be 10 dBm. Or you can find that power expressed in dBW, watt. In this case, you have to convert the milliwatt into watt. So this will give us 10 log base 10 of 10 times 10 to the power minus 3, or 10 log base 10 of 10 to the power minus 2, which is minus 20 dB watt. Okay, minus 20 dB watt. Both of these representations are correct and precise, but usually because of the powers, when it comes to electronic devices, the power is in milliwatt scale. It's more convenient to use the first notation here instead of the second notation. This is good for power applications, electric power systems, where the power is very high. But this is good, more convenient for the power calculation in electronic devices. Most of the times they are in milliwatt scale. Okay. Now let's define the voltage gain calculations. The gain expressed in dB for the voltage will be 20, not 10, times log base 10 of the output voltage, for example, divided by the input voltage. Why we have a 20 here instead of 10 as we had before in the power calculation? Because the voltage is proportional to the square root of power, or power is proportional to the square of the voltage. If you look at the slide, you have the power related to the voltage square, as we know. Yeah. So if you have an input output voltage equal to 3 volts, an input voltage peak value equal to 3 millivolt, we can express the AV gain first in decimal to be VO divided by V input, which will be 10 to the power 3 volt by volt. Or we can express this gain in terms of decimal scale to be 20 log base 10 of the 10 to the power 3. That would give us 60 dB. There is no unit here after dB because this is again a ratio of voltage by voltage. Okay. Any questions so far? We'll move on to...
No, I don't have any questions.
Okay, thank you. Now for the cascaded structure of amplifiers. We have multiple stage amplifier, and you find the magnitude of the overall gain to be the multiplication of the individual gains provided by the amplifier stages. We know this result. And in decimal, you just multiply the individual gains of individual stages. And how to find these individual gains, you follow the procedure we described in lecture in chapter 5 for BJT amplifiers, and in chapter 8 for FIT amplifiers, where you convert the stages into a two-port network models, and you connect them. After that, you find the gains of individual stages. Now, if you have this decimal value of the overall gain, you can find the overall gain. I'm now talking about the slide in terms of dB. And instead of multiplying decimal values to find the magnitude of the overall gain, you can just add the dB gain provided by each stage individually, and the proof of that is very trivial. So for example, to find the first gain of the first stage, you just need to take the gain provided by dB first stage, would be 20 log base 10 of the magnitude of the voltage gain of the first stage, like this. And you follow the same procedure to find the other gains, and then you add them. Why this is true? Because we said before that log base 10 of x times y will be log base 10 of x plus log base 10 of y. So we convert the calculation of the log here into a sum of individual logs. Using this principle, the proof of that equation is very trivial. Now we have a table to the right that shows different ratios of the output voltage to the input voltage, or gains, their expression in decimal and their expression in decibel or dB scale. Okay, please look at this table, and if you have anything, let us discuss it. Okay. Okay, so one of the good applications of what we are talking about now is the human auditory response. The sound pressure given in dB. Pressure is like voltage, it's like signal. That's why when we express that, the pressure in dB, we use a 20 P pressure, PR, just to distinguish that from power. This is not power, this is pressure, like a voltage signal. That's why we have a 20 here instead of 10. When you do the dB calculation, instead of 10 we have a 20, which means that the pressure is like a voltage signal. Log base 10 of the pressure P, RE, divided by a reference. The reference pressure is the 0.0002 microbar. This is a unit of pressure, bar. That 0.0002 microbar is the threshold level of hearing. In order to hear any sound, the voice pressure should be above that threshold. The human response to the sound is not linear. It's following logarithmic scale. Yeah. There is a table 93, very good table. If you like to learn more about this, please go through that table 93 in the textbook. Yeah. We have this example. It asks us actually to use the things we just described in the previous slides. Please please go through this example. We'll discuss it together. So for part A, explain to you graphically what we have here. We have an amplifier that has input terminal here, output terminals here. Okay. We connected the speaker to the output terminal. The speaker is the load, which has a 10 ohm resistor. The output power delivered by this device, P output, would be rated at 40 watts. The first part asks us to calculate the input power. We need to find the input power, I, input power. For full power output, if the power gain is 25, full power output means that the power delivered to the speaker would be the rated value, which is 40 watts. So with the gain of the power given to us, we need to get the input power in order to provide the full power to the output. The gain in dB of this power is 25 dB, and this would be the 10 log base 10 of the output power divided by the input power. We need to find Pi from this equation. So with some calculations, you will have Po divided by Pi equal to 10 to the power 2.5, or the input power would be the output power, which is 40 watt, divided by 10 to the power 2 to the power 5. Okay. So doing the calculation of this would give us 126.5 milliwatt. Please do verify that if you have calculator, that the input power would be 126.5 milliwatt. Verified? Okay, very good. Very good. Okay. Okay, thank you. So now the second part. Please go through the second part. We should be able to find the solution for it based on what we have here on this graph. Now, second part, just to explain it to you, we need to calculate the input voltage, V input, for the rated output. Rated output means that the rated output voltage. We can get the rated output voltage from the rated output power and from the load. Okay, we can get that, right? The rated output voltage would be the square root of the rated output power times the resistor. Okay. The amplifier provides us a voltage gain for a dB, so we should be able to get the input voltage from that. Please tell me if you were able to get the input voltage for the second part. Okay, thank you, Sujan. Thanks, Eduardo, Chris. Thank you. Courtney, thank you.
Got it.
Thank you so much. Yeah, you are right. It's good to practice that, yeah. What about the rest of the class? Okay, very good. Okay, thank you. Okay, thank you. Still we have to hear from Andrew, Hani, I think Richard, Sam. Okay, good. Taylor, Victor. Okay. Victor. Okay, so I think we are good to move to next slide. Now section 4 talks about general frequency considerations. Let's follow up on the slide. Frequency response of an amplifier is the frequency range in which an amplifier will operate with negligible effects from external capacitors and device internal capacitors. And this range is often called mid-range. at frequencies below that mid-range, the external capacitors, which are the coupling capacitors and bypass capacitors, which are the external capacitors that we add to the circuit in order to design the amplifier. Okay, these external capacitors lower the gain at low frequencies. So at very low frequencies, the gain provided by the amplifier degrades because of these external capacitors. On the other hand, at high frequencies above that mid-range, internal capacitors, parasitic or stray capacitors associated with the construction of the BGT or FIT, the physical structure of them, lower the gain. So we have that mid-range. We will have a slide on that, but just to explain to you the concept we are talking about here. The amplifier will have a frequency response which says over the frequency F. The gain in magnitude AV provided by that amplifier is not always flat at the maximum value. Over some frequency range, which goes from here to here, the gain will be maximum. But if you decrease the frequency below a certain point, the gain will decrease. And if you increase the frequency of the input signal above a certain point, the gain will also decrease. So this is a typical frequency response of an amplifier. Ideally speaking, we would prefer to have something like this. Gain that is constant, like this straight line at any frequency will give us the maximum gain, but this is practically impossible. Okay. The reason for having a decayed gain here at low frequencies below this threshold. These are low frequencies, closer to the 0 Hz. The frequency increases in this direction. The reason for seeing this decay in the magnitude is because of the external capacitors, the coupling and bypass capacitors we add to the amplifier circuit. And we add these external capacitors in order to separate the DC from the AC, right? The DC from the AC. These are important components that we have to include when you design the amplifier. On the other hand, the reason of saying the decay in the amplifier here at the high frequency range, at higher frequencies, is because of the internal capacitors that are due to this structure of the JFET and BGT. The capacitors that will decrease the gain here are in picofarad range or nanofarad range maximum. They are very small, but they are significant at high frequencies. The capacitors that decrease the gain here are usually in microfarad or maximum in millifarad range. Okay. In addition to this, which is a frequency response of a single stage amplifier, if you have a cascaded amplifier structure, each of the stages, each of them will have a frequency response like this. And they don't have to have the same cutoff frequencies, the same thresholds at which the response will start to decay. Yeah. So the cascaded structure is expected to always decrease the frequency response or decrease the mid-range of the response at which the gain is maximum. Why? Because if you have cascaded structure, we need to multiply this response with the second response, with the third response, and so on. So the dominant cutoff frequencies at the lower frequency range, at the higher frequency range, cutoff frequencies at which the gain start to decay will be determined based on that intersection of the cutoff frequencies of individual stages. So the second stage could have a response like this. The third stage could have a response like this. If you cascade all plus one, okay, which makes sense. Now, in more details about the low frequency range, this range here. We said that these external capacitors are the reason of saying this decay and the voltage gain. These are big capacitors. To understand more, look at the table there. The table shows us the impedance Z of these capacitors would be the minus J times the reactance of these capacitors. So the reactance of the capacitors the reactance of the capacitor will be 1 by 2 pi times F times the capacitance of the capacitor. Okay. Now the table shows these values, the XC values for a microfarad capacitor. 1 microfarad capacitor is the value of the capacitance here at different frequencies F. Again, these are the frequencies of the input signal that we need to amplify. Okay. So at different frequencies, as you see there, we see dramatic change in the value of XC or the impedance of that capacitor. We are talking about sinusoidal signals. Okay. So at low frequencies, as you see there, the XC value is apparently very high. It is noticeable. It cannot be neglected. Okay. Because of this high impedance of the capacitor, you will see a decrease in the gain provided by the amplifier. At higher frequencies, starting from 100 kilohertz and above, when this F is 100 kilohertz and above, the impedance of that capacitor is very small, as you see in the table, and in this case it can be neglected, as we did in chapter 5 and 8, when we said when you do the AC analysis you short circuit the capacitors, external capacitors, right? We did short them because we didn't discuss that in details there, but we did short them because the impedance of these capacitors at the operating frequencies are very small, so we can replace them by short circuit. So the external capacitors that are large in size, 1 microfarad, 10 microfarad, and so on, are responsible of decaying or decreasing the voltage gain at low frequency range. And the reason for that is very clear from the table. Any comments, any questions so far? Clear? Is it clear? Everybody?
I had a bit of technical difficulties when you were drawing that picture at the top. Could you just go one more time over what the different lines mean?
Okay. The first one here represents a typical frequency response of a single stage amplifier. This one. Okay.
Okay.
The second one down. The second one represents a frequency response of another amplifier, or the second stage. We have a cascaded structure. The third one here represents the frequency response of the third stage individually. Okay. We said that when you cascade them, when you connect them in order to produce a cascaded amplifier, the frequency response of the cascaded structure will be determined by the intersection of these three frequency responses. Okay. So the structure, when you connect them, okay, will have a frequency response which will follow the third one here, because this is the frequency response. Okay. This one, last one, which is, this is the frequency response of the whole structure. The cutoff frequency of the cascaded structure should be determined. on the highest lower frequency cutoff frequency and the lowest higher cutoff frequency. Okay, and we said that ideally speaking, we would like to have an amplifier that always provide us the maximum gain at all frequencies, which is in this case will give us a straight line for the gain, okay, at any frequency of operation. This is practically impossible. Okay, and we have now two rules. We have the mid band here, and this is the mid band. Okay, we have figures, so we'll explain that on figures later on, I think in the next slide, on the next couple of slides. So this is the mid band at which the gain is maximum, and we have also here two bands or two regions. Okay, these two regions represent a decade gain, right, as function of frequency. This is the lower frequency range, and this is the higher frequency range. It's not recommended to operate the amplifier in these two ranges because the gain provided by that amplifier would be lower than the maximum gain possible. Okay, we said that the capacitors that are externally introduced into the amplifier circuit are responsible to decrease the gain at lower frequency range here, and the capacitors that are associated with the structure, internal structure of the JFET and FET, JFET and BGT are responsible to determine this kind of response. Okay, and we started discussing how the low frequency range, this range, would be affected by the large capacitors that are used to decouple the DC from AC, the bypass and coupling capacitors in the amplifier, the external ones. We just explained that in details. Now the next slide. The next slide. Consider this range, the high frequency range. We said these smaller capacitors, because of the internal structure of the device itself, are responsible to decrease the gain at these frequencies, and the reason for that is very clear when you consider the table here. Okay, so we're doing the same. We find the impedance of the capacitor, but now the capacitor value would be very small. And instead of 1 microfarad external capacitor, the internal capacitors are usually in picofarad range. So the example given to us in the table is for a capacitor whose value is 5 picofarad. And the objective now is to evaluate that reactance of the capacitor or the impedance at different frequencies to see how these impedances changes with the frequency change. So looking at the table, at low frequencies, you see at low frequencies up to 10 kilohertz, the reactance of the capacitor is very large, or the impedance of the capacitor also is very large because they are proportional to each other. In this case, we can neglect the effect of these internal capacitors because they will appear as open circuit. Okay, open circuit. They will have no effect. On the other hand, at higher range of frequencies, above 100 kilohertz, okay, we start to see this frequency response. Why? Because the impedances of these small capacitors cannot be neglected anymore. We have to consider their effect. The consideration of their effect is reflected into a decrease in the gain provided by the amplifier. Okay. Last thing is the mid-range, this range, the fixed gain here. Yeah. In the mid-range, we neglect the effect of both external capacitors and internal capacitors. External capacitors, when we operate here, exactly here, are replaced by short circuits. Internal capacitors are replaced by open circuits. So their effect is negligible. That's why when we did the gain calculation of the amplifiers in chapter 5 and 8, we did consider circuits that are purely resistive circuits, right? The circuits were purely resistive, right? We didn't consider the capacitive effect of these capacitors. Why? Because we did neglect them based on our based on our adjustment of the input frequency of the signal to be amplified. That frequency was here exactly in the mid-range. Okay, so we didn't consider the effect of external capacitors and internal capacitors because we were working here in the mid-band. Okay, yeah. Any questions so far? Please ask if you have any question before we move on to the next slide. Okay, clear? Everybody? Yeah, I hope so. We'll move on. Yes. Thank you so much. Thank you so much for the response. Now we have the figures that will explain what I said more clearly. Exactly similar to the figures. Oh, not similar because this is it's not a figure anymore, but same figure we were discussing. You see this figure? Now forget about the other two. Just focus on the first one. Okay, the first figure. The first figure shows us the voltage gain magnitude, which is the ratio of the output voltage to the input voltage magnitude. Okay, there are three regions: the mid-band region, where we define the bandwidth of that amplifier; the low frequency region here to the left, and the high frequency. Let me see, try to. This is the low frequency region here and the high frequency region here. Okay. Again, a decrease in the gain because of the external capacitors, decrease in the gain because of internal capacitors. And between them, here we have the mid-band at which the gain is almost constant at maximum value. Okay. So always we would prefer to utilize that amplifier in order to provide us the maximum gain. Does not make sense actually to buy an amplifier and use that amplifier to operate here, right? Because you will not get the full benefit of the amplifier, which is amplification, right? Okay, so now we define important things based on what we have here. The first thing is the bandwidth of the amplifier. The bandwidth is the difference between two frequency thresholds, one to the right and the other one to the left. Okay, so the bandwidth BW bandwidth is the FH minus FL. We will define these now. The FH and FL represent the cutoff frequencies of the amplifier. This is H from higher, and this is a cutoff frequency of the amplifier, and FL from lower, cutoff frequency. Okay, so in order to know the bandwidth over which the gain of the amplifier will be constant, we have to know these two frequencies. Okay, the higher cutoff frequency and the lower cutoff frequency. Per definition, these cutoff frequencies are defined as the frequencies at which, we'll draw this again for you here just to be clear. This is the maximum gain, which is the gain AV at mid-band, sub-mid, like this. Okay, we define the lower cutoff frequency, FL, to be the frequency at which the gain will be the mid-band gain maximum divided by square root of 2. And same thing, we define the higher cutoff frequency FH to be the frequency at which the gain is the maximum gain AV at midband divided by square root of 2. Okay, so this is how we get these frequencies. If we know these two frequencies, the cutoff frequencies, we can get the bandwidth of the amplifier. Okay, why we have square root of 2 here? Because they were defined in terms of the power. The lower cutoff frequency is the frequency at which the power is 0.5 of the maximum power. 0.5 of the maximum power. Okay, and we know that the voltage is related to the square root of the power. So we need to square root that 0.5 in order to get what? To get the 1 by square root of 2 here. Okay. In dB scale, if the maximum gain here in dB is 10 dB, a decrease of 1 by square root of 2 represents a 3 dB decrease from the maximum, which means that the lower cutoff frequency and upper cutoff frequency will be measured exactly at the 7 dB gain level, 7 dB, because the 1 divided by square root of 2 would give us the 3 dB difference between the maximum and the points at which we get the lower cutoff frequency and upper cutoff frequency. There is a 3 dB difference between these two. Okay. Any questions? Okay. Now the sketch you see here, we will learn how to construct this. This is a very famous sketch, which is the baud plot. The baud plot usually shows the x-axis, the frequency range in log scale, and the y-axis, which is the gain, usually voltage gain, in dB scale or decibel scale. Okay, it is not shown here in dB, but usually this scale is given in dB scale. That's why it is a baud plot, and in most cases all amplifiers in the market have this frequency response already sketched to you, and in that sketch you will see the x-axis, which is the frequency axis in log scale, and the y-axis, which is the gain provided by the amplifier in absolute value magnitude in dB scale. Okay, we move on to next slide. This is another slide that shows us the 3 regions we were talking about again. Midband region here. This is the midband region. Lower frequency range here, and upper frequency range here. We have the cutoff frequencies F high and F low. We get these based on what we just discussed. These frequencies are obtained at a gain which is 1 by square root of 2 of the maximum. So in this case, if the maximum gain provided by this amplifier is 1 at 0.707, which is 1 by square root of 2, we have to be able to get the F low and F high. Okay. Instead of using a decimal values here on the y-axis of the gain provided, we can express this curve in dB scale, as you see here. So the maximum gain here 1 would be a 0 dB threshold. 0.707 will be minus 3 dB. That's why we said there is a 3 dB difference always between the gain at the maximum value and the gain at which we have the lower frequency and the higher frequency cutoff frequencies of the amplifier. There is a 3 dB gain difference, okay, and so on. Okay, that's why you see these values in negative dB, because they will be corresponding to values of the gain that is below 1. Okay. The last thing to talk about this figure is the normalization of the gain. Usually we express the gain as a ratio here with respect to the maximum value. Okay. For example, just to give you an example about this, if you have in decimal value, if you have this frequency response representing certain amplifier, this is AV, magnitude gain, okay, whose value is 100. Okay, what you can do is resketch the same frequency response without changing anything, but with the maximum value normalized to unity. And in this case, the y-axis, the AV, would be the AV magnitude normalized by the maximum 100. Okay, and this 100 in this case would represent the voltage gain at the mid-band, sub-mid, which is the maximum value. Okay, so this is typical to see that the amplifier has always a maximum value of 1. Okay, but we have to be careful when we consider this. The 1 here represents the normalized maximum value. It is not the actual gain provided by the amplifier, normalized maximum. Okay, because the gain will be normalized by its maximum value. Okay. Let me see if you have any questions here. Anybody else get an error message and no longer hearing audio?
I have a question.
Yes.
So the normalized version, sorry if there's feedback. The normalized version, is that the Bode plot, or is the Bode plot the one that is not normalized?
Both of these are Bode plots. The first one shows the y-axis normalized in decimal. The second one shows the y-axis normalized in dB, decibel, and both of them are normalized because, as you see here, the maximum value of the gain is unity, right? So the AV is already normalized by its maximum, and in dB the maximum value would be 0 dB, which is just log 10 log base 10 of the unity, which is 0 dB. Does this answer your question, Hannah?
Not quite. It's helpful, but the last slide, the plots were not normalized.
Yes.
And you mentioned that those were like Bode plots, but is the normalized version just as much a Bode plot as the unnormalized version from the last slide?
Yes, absolutely. In the previous slide, the values were not normalized, you are right. Still, this is a Bode plot, but the y-axis is not normalized, which is fine. A more, let's say, a more professional way to generate the Bode plot is to do the normalization of the y-axis like this, more professional. But this does not mean that the previous sketch is not a correct frequency response sketch. Okay?
Okay.
Yeah, so the normalization is something that would be recommended when you do the plot, is to normalize the y-axis by the maximum value of the gain provided by the amplifier. But if you don't do so, it should be fine also, because that normalization would help us actually to reduce the size of a sketch. Instead of if you wanna sketch this in decibel, let's say, and the maximum value was 100, okay, the 100 is something very big like this. So sometimes if the gain is very large, right, you have to in order to reflect that high gain accurately, you have to expand, right, the sketch very wide, right? That's why the normalization will help us always to sketch them into scale and say that the maximum here is unity, and that maximum is the voltage gain AV divided by the maximum value, by the max. Okay, in magnitude. Okay, this way I think this is more professional way to express the y-axis, let's say. Okay, is it clear now?
Yes.
Okay, very good.
Thank you.
Yeah, sure. Any other questions? Okay, we move on. Now we discussed the magnitude of the voltage gain, but also the voltage gain has a frequency, has a phase response. If you remember, we said before that the common emitter amplifier will provide us a 180-degree phase shift between the input and output. And same we said for the common source amplifier using FETs. So 180 degrees, as you see in this figure, and within the mid-band, within the range of the bandwidth of the amplifier from F low to F high. Apparently this amplifier providing us 180-degree phase shift. You see that? Where the output leads the input by 80 by degrees. Okay. But if the operating frequency of the input is not within this range, do you see, by the way, do you see the marker in the slide? Everybody, do you see the marker I'm using on the slide?
Yes.
Yes.
Okay, very good. So if the operating frequency is here or here, okay, the phase shift between the input and output is not necessarily to be the 180 degrees. Okay, for example, in this case, it could be higher here if the operating frequency is lower than FL, and it could be lower than 180 degrees if the operating frequency is somewhere here. Okay, so the constant phase shift between the input and output is only valid and is not changing as long as we operate in the mid-band. We operate within the bandwidth of the amplifier from here to here. Okay, and that phase shift will be changing as function of frequency here and here. And if you remember, I think Tristan, Eduardo, and Richard last semester had a project on the filter design, right? You remember that?
Yes.
And okay, and to remind you about the question of I think Hannah said that have you tried to investigate how the frequency would affect the phase shift between the input and output, right? Right, Hannah?
Yes.
Right. And now, Tristan, looking at this figure, we should be able to answer this, right?
Yes, correct.
Right. So we do expect that phase shift to change if we are operating here or here. But we don't expect that phase to change if we are within the bandwidth of the amplifier, right? From here to here. Yeah? I think this will answer, this will
When I'm
answer
doing
now.
the
Go ahead.
experiment, the phase shift still change within the bandwidth, but it's very, very small. But once you get outside, it starts to change dramatically.
Excellent, excellent. So you verified that already. Excellent, Tristan. Thank you
Yes.
so much for doing so. Yeah. So, any questions so far, guys?
This slide has FL and FH on them. Is it the same cutoff frequencies as a couple slides ago? Like same definition?
Yes, same definition. These are the FL, which is the lower cutoff frequency. This is FH, which is the higher cutoff frequency that we defined before. Same. So the bandwidth of the amplifier is still measured by taking the difference between FH and FL. This is the bandwidth here. So the bandwidth BW will be the difference between FH minus FL. Okay. Chris, I think, Chris, you hear me, Chris? I will try to turn him. You hear me? Just take a look at the comments of your colleagues. Yeah, you can keep it on, no problem. You have a nice actually.
I thought y'all might want to see me by now. Sorry,
yeah.
I hit the wrong button.
No problem. Yeah, I like the guys behind you anyway.
My wife teaches VIP on the side, and so I'm using her little area.
Yeah.
So
Yeah.
if y'all want to keep them on there, I got all sorts of stuff right now. Sorry.
Yeah. No problem. Yeah. Okay, guys. So when we come back after the break, we will solve this exercise together. Okay? We'll take a break about 10 minutes. We need to find the cutoff frequencies. We were given a sketch of a frequency response, and we are asked to find the low frequency response and high frequency response. Cutoff frequencies. Hello everybody, you hear me?
Yes, I hear you.
Okay, good. Okay, so please work this problem, at least part A, find the lower cutoff frequency FL, the higher cutoff frequency FH, based on what we have here. Now you were given that the value equal 10 to the power x times 10 to the power d1 distance divided by d2 distance. Okay, so this value is the value of the frequency. So just to explain this for you, when you do the calculations of the frequencies, you were given that the frequency value of frequency equal 10 to the power x times 10 to the power the ratio of d1 divided by d2. Okay. So you need to find the ratio d1 d2 first, and then power that to 10.
So when you're saying different functions, you're saying y then equals time shift diversion of y then?
Who is this?
Oh, might be me, I'm sorry.
Okay, because I hear Charlie, I think.
Sorry, I hear him too, but you guys don't have to. Let me turn my mic off.
Yeah, no problem, no problem. Okay, so this is the value for the frequency. You need to find the ratio of d1 to d2, and then use 10 to the power that ratio times 10 to the power x. X is the initial value of the range. So if you are given the range, for example, in the first case from 100, I think 100 to 1000, the x value will be the 100. Okay. Yes, which is x in this case equal to 2, which is the power of 10 to the power 2, the power of this 100. Okay. Anybody found the lower cutoff frequencies, higher cutoff frequencies? This is the value of the lower cutoff frequency here, and this is the value of the higher cutoff frequency. Okay, again, this is the value of the frequency that we need to find. This is the frequency value. So the first for the first case, as you see, the range starts from 100 here. So the x value should be 2. The second range starts from 10,000. So the x value should be 4. Any answers for part A? By the way, the higher cutoff frequency FH should be in kilohertz, not in hertz. Okay,
Wait,
good, Sir John.
the higher frequency, should that still be correct with 27,000 hertz? It would be same as 27 kilohertz?
Yes, 27.416 kilohertz, right. So there is a kilohertz missing here, so we have to just a type on the answer. This unit in here should be in kilohertz. Okay, in kilohertz.
Yeah, so just have that as a point. There's supposed to be a point right there. And instead of a comma.
Say it again, Tristan.
Okay, I do believe it's still correct because it shows right there 27, comma 416. So is it 27,000?
There is
This one
dots
down
in
here
there.
is 27.424. That's for the bandwidth. I know that's not going to be the exact same. But
Yeah, that's why the unit should be in kilohertz.
okay.
So 2.7416 times 10 to the power 4 is 2.7416 times 10 times 10 to the power 3, right?
Yes.
Which give us 27.4 kilohertz.
Yes. Okay.
Okay, verified the first part. We have Surjan said yes, Tristan I think agree. And what about the rest?
I'm good.
Excellent, very good. And okay, Hani, thank you. Okay, Sam, good. Andrew, good. Xavier, good. Taylor, great. Richard, good. Andrew, good. Okay, excellent. Saul, good. Victor, still we need to hear from Victor today. And I think Richard Horton is not here today, right? Is not attending. Yeah, okay. Sam. Okay. Okay, no problem. Okay, guys. Yeah, I fully understand that. Yeah, should not be a problem. Yeah. So part is good. What about the second part? Find the bandwidth. Bandwidth. Once you get these frequencies, FH and FL, the bandwidth is just the difference between them. FH minus FL, right? So this will solve part B. Sketch the normalized response. As we said, you just normalize the y-axis here. You normalize these values by the maximum, which is 128. That's why we get the response down, where the maximum would be now 1 instead of 128. And the cutoff frequencies will be at now 90.5 divided by 128, which is 1 by square root of 2 as expected. So this is the threshold where we expect to have a difference in decimal between these two values of 1 by divided by square root of 2. Everybody's okay with this exercise? Okay, good. Okay, thank you so much. So we move on to, okay, thank you. Move on to now section 6. We start now our analysis of how we can find these cutoff frequencies from a real amplifier circuit. Okay, start with the low frequency analysis. Now this analysis will be repeated again and again for any amplifier in the next sections, the procedure of analysis that we are going to do here in this section. So it's good for you to pay more attention to this section, please, because again the procedure of analysis will be repeated in the coming sections, the same procedure. Okay, so this section talks about the low frequency analysis, the Bode plot, how you generate the Bode plot, or how you can find the cutoff frequencies. Okay, so we have an amplifier circuit here. Apparently this is a common common emitter, common collector, common base, common source. What type of amplifier we have here?
Is it emitter follower or common emitter?
Yeah, okay, yeah, we have a common emitter. Why? Because the emitter now AC will be, this will be short circuit, right? The capacitor, apparently. So this is common emitter, where the input from the base and the output from the collector. Okay, this is a common emitter amplifier. Still, we didn't connect the source to be amplified at the input side and the load at which we're gonna deliver the amplified version of the input. Here, there is no RL, there is no source. Okay, so for this amplifier, we have how many external capacitors here?
Three.
We have 3 external capacitors. Thank you. And these are the CS capacitor, S from source, because this capacitor will be connected to the source side. The CE capacitor, because this capacitor is connected at the emitter side. The CC capacitor, C capacitance, sub C, because this capacitor is connected to the collector side. So we have 3 external capacitors. We said before, the low frequency response of this amplifier will be decided based on the cutoff frequencies produced by the presence of these 3 external capacitors. Okay, so we need to find the cutoff frequency of these individual capacitors and then intersect the values we obtain in order to find the cutoff frequency of the whole amplifier, the lower cutoff frequency. Okay, we start the process by investigating the effect of these 3 capacitors individually, one by one. Okay, now let's focus on this capacitor in here, the first capacitor here, this one. What is the effect of this capacitor on the response of the amplifier? Okay, on doing so, we are concerned about how the output voltage taken at right after the capacitor will be related to the input voltage. So this is the CS capacitance, and we want to know what is the relation between this voltage at after the capacitor to this voltage at the input of the capacitor. To get this voltage at the output of the capacitor, looking from this side of the amplifier, back to the presentation, from this side of the amplifier, the output voltage will be measured exactly at this node, right? Exactly at this node. we are doing AC analysis. In the AC analysis, the DC source will be short circuit. Okay, so these two resistors will be connected in parallel. In addition to that, we will replace the diode, which is here, by its internal resistor, whose value is beta times Re. Okay, or we can complete the structure of the circuit, AC circuit, by adding the R1 resistor here and then the R2 resistor here in parallel, and we will have now the resistor representing that diode between the base and emitter, whose value is beta times Re. So this is the input portion of the AC circuit, the input portion. So the output voltage at this moment after the capacitor is the voltage measured across these three parallel resistors. Okay. Now looking from this side, we find that the input resistor of the amplifier, what we see to the right of this capacitor, this R input, is the parallel combination of R1 with R2 with beta Re. Okay. Now the circuit could be simplified into this form. It is just a capacitor and an input resistor or input impedance of the structure, whose value will be the parallel combination of these two, and we were concerned about the ratio of the output voltage to the input voltage of this specific capacitor. Okay, we need to know how that output voltage changes. Okay, by changing the input frequency in here for this specific capacitor. Now the procedure we are doing would be repeated for the other two capacitors. Same procedure. When you consider the effect of CS, this capacitor, we short circuit the other two capacitors. We neglect them like a superposition principle. Okay, so first we consider the effect of this capacitor. These two will be short circuit. Second, we consider the effect of this capacitor. These two will be short circuit. Third, we consider the effect of this capacitor. These two will be short circuit. And every time we are concerned about studying how the output voltage at the output of the amplifier, at the output of the capacitor, would change by changing the input frequency at the input of the capacitor. Okay, this is what we are concerned about. So, given this now very simple RC circuit, can we get the output voltage in terms of the input voltage? The answer should be yes. Okay, we find for that simple circuit, we find that the output voltage would be, using voltage division, the input resistor divided by the input resistor plus the impedance of the capacitor, CS, times the input voltage. Okay. Now the voltage gain of this network would be defined as VO divided by VN equal to R input divided by R input minus J times XC, which is the reactance of the capacitor, whose value is 1 by 2 by F times the capacitance value. Yeah. Now the next step, we can just divide both sides by RE in order to get 1 up there divided by 1 minus J 1 by 2 by F C times R input. So this is what we have now here. Okay. So the voltage gain would be 1 by 1 minus J. We have 1 divided by this term. Okay.
Excuse me.
Yes, go ahead.
Are we assuming that the resistor equals 1? Is that how we got that?
Would you please say it again?
Sure. So I noticed you replaced RI with unity with 1, and I was wondering why you were able to do that.
replace which I?
R sub I in your equation there at the bottom that you wrote.
Right.
Why did the
Yeah.
R's turn into ones?
Oh, yes. Okay. So what we did here, we did multiply by. Okay, explain it another way. What we did, we take this down. So we'll have this term divided by Ri like this, right? And we will have one up. Okay. Then we have Ri divided by Ri1 minus Jxc, which is this term, divided by Ri. Is it clear? Or
Yeah.
take Ri common factor from denominator, take it as a common factor, and you will have Ri down, Ri up, that will cancel, and you end up down having 1 minus Jx divided by that Ri.
Yes, I understand now. Thank you.
Okay, sure. Now we have now this voltage gain between output and input. Okay, now looking at this result, we can tell whether the RC circuit we have there is operating as a low pass filter or high pass filter, which means that whether that network would pass high frequencies or low frequencies by simple check. That simple check is to evaluate the voltage gain at two frequency limits. The first one, when the frequency is 0 Hertz at very low frequency, the gain apparently when the frequency f is 0, this term will be 0 down, so 1 by 0 will be infinity, so the voltage gain will be 1 divided by infinity, which is what?
0.
Which is 0. Very good. So there is no output voltage when the frequency is 0 Hertz. Now on the other hand, when the frequency goes to infinity, very, very large frequency, what will happen to the voltage gain here? We have f very large, 1 by f is very small, 1 minus j, very small number, is almost 1. So we'll have 1 divided by 1. The gain will be approximately approaching 1 unity, which is the maximum in this case, right? So based on what we have here, we can tell that, okay, this network will pass frequencies that are very high and will reject frequencies that are very low. In this case, we can say that the network will operate like what? A high pass filter that will pass high frequencies and reject low frequencies. Okay. The other justification of the result we have here is that looking at the network at no frequency, this capacitor, the capacitor in here, would be replaced by what? An open circuit, right? Because we know the capacitor is open circuit for DC. When the frequency of this signal is 0, DC, like 10 volt we have here, 10 volt input that has a frequency 0, the capacitor will appear like an open circuit. There is no current. The output will be blocked, right? Because of this open circuit. The output voltage would read 0 volt. Okay? There is nothing at the output. On the other hand, at very high frequencies, the impedance of this capacitor will look like a very short circuit. The impedance, which is minus J times XC, will look like a short circuit, very small impedance. So we can short circuit the capacitor to get an output voltage that is equal to the input voltage, this input voltage, when the frequencies are very high. Okay, so this very simple network is operating as a low pass filter. Okay, good. Now, based on the AV value we have here, we can find now the cutoff frequencies of the low pass filter. The cutoff frequency of the low pass filter is defined to be the frequency at which the gain will be 3 dB below the maximum. So this is the cutoff frequency. Okay. The high pass filter is expected to have a frequency response like this. Yeah. It passes high frequencies and neglects or rejects low frequencies. Okay. So the maximum gain AV magnitude value is 1, and at the lower cutoff frequency of the high pass network, the gain would be 1 by square root of the maximum, which is 1 by square root times 1. Okay, 1 by square root of the maximum. Okay. Now the objective is to find this cutoff frequency. Why we have here a lower cutoff frequency? Because this is a high pass filter. Okay, it has no higher cutoff frequency. Always the gain will be unity as long as that frequency is much higher than the lower cutoff frequency. There is no FH here. Okay, but there is FL. There is low cutoff frequency. Okay, because the gain is increasing. You see, if you increase the operating frequency of the input voltage, the gain is increasing. Okay, up to a certain frequency here where the gain will be unity. That frequency is maybe 10 times, 20 times, 30 times that lower cutoff frequency. The lower cutoff frequency provides us a gain which is 1 by square root of 2 of the maximum, or 0.707 of the maximum. We need to find FL. Where we get that FL from? We get that FL from the magnitude of AV. We have to get the magnitude of AV. We just found that AV expression, which is the ratio of VO divided by V input, as 1 divided by 1 minus J, 1 by 2 by times F times C times R input. Okay, what is the magnitude of this complex quantity? The magnitude of the complex quantity AV magnitude will be 1 divided by square root of the real part squared, which is 1, plus the imaginary part squared, which is this term, 1 by 2 by F times C times Ri, all squared. Okay, so this is the magnitude of the voltage gain. Now we need this magnitude to be equal to 1 by square root of 2, and then solve for that frequency F. Solve for F at which this condition is satisfied. Okay, so we need to solve for F that satisfy this condition. Okay, by doing so, very simple, looking at this expression in here, in order to get this term equal to 1 by square root of 2, we have to have 1 by 2 by the FCRI simply equal to 1. If this is satisfied, we will have down square root of 1 plus 1. Okay, 1 plus 1. Okay, so we solve this for F, which is the lower cutoff frequency, and we find that the lower cutoff frequency should be 1 by 2 by times the C value times Ri, which C? The CS value. Okay, for the capacitor CS. So this is the lower cutoff frequency value. Okay, if you have the numerical values for CS and Ri, you can plug them there in order to find the lower cutoff frequency. Any questions?
I don't have any.
So in your formula, a couple of lines above, was the F, when you wrote that, was that F sub L, or it's still just regular F?
Up to here, okay, this is a general value, general frequency, any F. But when we equate this equation to 1 by square root of 2, the resulting value of F should be exactly the lower cutoff frequency value, because we know at this specific frequency, okay, the magnitude of the voltage gain would be 1 by square root of 2 at this frequency.
That makes sense. Thank you.
Yeah, thank you so much. Another questions? I think we run out of time today. Please, if you have any question, do say them now. If you have any question.
Can our teams turn in our reports through D2L? Is there a Dropbox for that yet? Or would you like us to email them to you?
Yes, I think there is a submission folder in the D2L where you can upload your lab report in there.
Okay.
Let me know if you couldn't see that folder. Okay.
I just found one. It says E321 Lab 3. There is one submission.
Yes. Yeah. There is. Yes.
Okay. This will be the 4th lab, the one that we're working on right now.
Yes. You are doing now the 4th lab, and whenever you have the 4th lab ready, just do the submission for that. I don't want to. I mean, we are in a difficult situation anyway. I don't want to actually put a very hard deadlines, but what we expect you usually to do is submitting the lab report after 1 week from finishing the experiment. I will be flexible in the submissions, no problem. If you face any difficulties, internet difficulties, or you don't have a scanner, or whatever kind of things that prevent you to meet the deadlines, please always let me know. Just email me, we'll find a solution.
Thank you.
Yeah. Thank you, guys. Have a good day, and please feel free to contact me if I can be of any assistance to you. Okay. Thank you so much. Have a great day. Thank you.
Thank you. You too.
Thank you.
Bye.
Yeah.
See you
bye.
guys this afternoon.
See you. Bye.
Have a good day, guys.